So what we started to do here is that we started to look at the RC circuit math diagram. And to give you an overall view of the whole process, this is not what I would call problem-solving strategies. But this is essentially to give you a view of how you have to attack every circuit. So here we go. The overview is that before the switch is thrown, you determine VC of 0, 9. The switch is now thrown. Your number one job is to convert this RC circuit into a Thevenin circuit. That means you got to calculate VOC and RTH. So that's all the way back into chapter 5 here. So that means, remember, if I have constant sources, I could just short out the source. But if I have a dependent source, I got to place a short at the capacitor and then do the calculation to get our RTH. So you got to pay attention to that. Then we solve the Thevenin RC circuit. Then we undo the Thevenin circuit, and then we solve the problem. So just kind of thinking offhand, look at that. Circuit number 1, circuit 2 and 3, circuit 4. One problem could have 4 different circuits that you got to solve. Okay? So here we go. So I picked an easy circuit. Why did I pick an easy circuit? Because it's fast to do right now. So the switch, before the switch is thrown, the capacitor is in steady state. What did I do? I just used VDR to get the voltage of the cap, which is the same as the voltage across the 3. So it looks like that. Okay. Then after the switch is thrown, I kill off resistor 1. Now, my job is to convert this into a Thevenin RC circuit. So here I go. How do I do that? I determine VOC. I determine RTH. The fact that this is a constant source means that I can calculate RTH this way. So here I go. So you could see here in this case here that I kill resistor 1, so now the voltage VOC at the open, because that's where the load is at, has to be the same as V3, so I get VOC. When I determine RTH here, it's at the load opening, and you can see that I have 2 resistors in parallel, so I go to 2 resistors in parallel. So now, regardless of how complicated the circuit is, I'm always going to deal with the circuit. Let me say this one more time. This is the only circuit we solve for a constant source. If it's time dependent, then we got to do this process every single time. Okay, so for a constant source, it's always like this. So now, what am I going to do? I'm going to apply KVL to determine the first order equation. What do I mean by first order equation? First order differential equation. So I use KVL. I replace the current with the current of a capacitor because they're in series. I get this equation. I rewrite. I get that equation right there. Now, because this is similar form to the inductor, I'm going to use a dummy variable x so that I can apply this immediately to the inductor. So I set x to VC, tau to the RC constant as always, and then this effective source constant I just call k. So I plug it in here, manipulate the variables so that I have all the x's on one side, time separated from x. I integrate, I get a log. I get minus t over tau plus the integration constant, right? That integration constant is important because of what? That initial condition. That initial condition sets the value of A. So then I take the exponential of both sides, I get this. So now I'm going to apply boundary conditions. Why do I call this boundary conditions? 1, there's a condition at t equal to 0. 2, there's a condition at x equal to infinity. Initial conditions talks about just initially, but here we're talking about the bounds between the solution can exist. So what I do here is that I'm going to define these variables, tau, k, and a, in terms of my boundary conditions. X equal to 0 minus, what is that guy? I would have solved this in this circuit. X equal to infinity, I mean by what? I mean by VOC, because that's what the circuit, the capacitor voltage has to be. And then what I end up doing here is that now I set 0, into this solution. I get the 1 for the exponential. I set t equals to infinity here, which kills off this term. So I get that. So all I'm going to do here is I'm going to rewrite infinity for that, a for this. That's the general form right there. Now it turns out that this is the mathematical form. And the book, you'll see, will call this the natural response, and that's the forced response. I'm going to disagree with the book. And I think the reason why I'm going to disagree is that when we have time-dependent sources, the natural response should be the exact same, or the homogeneous solution should look exactly the same. It doesn't in the language that the book does, even though it's natural to think about the way the book does. So I'm going to apply this to the cap. So I punch in my values, and here I go. That's my solution. Now remember what I said here. This is best for calculational form. When I go to calculate things, what do? I use this form. But when I physically start to interpret it, that's not the way I use it. Okay? So let's go do this now. So what I want to do now is that I want to interpret all of this. I want to erase, add more stuff, and then we need to start looking at calculations. You know, I don't know if I ever told you this, but I remember when I was at college at the University of Arizona, I had a left-handed instructor. Back then, we didn't have whiteboards, we had chalkboards. This guy was good. This is what this guy would do. He would write beautifully and erase at the same time. Now, I could barely chew gum and walk at the same time. And this guy was freaking amazing. You know, he wouldn't miss a step. Okay, so now what we want to do here so when I look at this thing here, I want to start interpreting what we're talking about here. So remember, this physical interpretation of the circuit makes the differential equation real. We are now setting up intuition, really. So when we get to the end of the chapter, as well as chapter 9. So you really got to ground your intuition well, right here. Otherwise, it's just mathematics. I'm not interested in mathematics. I'm interested in describing circuits and their behavior. So let's talk about, I want to physically interpret RCC. So the first thing that we could say here is that the solution, which they typically call the response, satisfies, you know, the boundary condition. What do I mean here? So if I look at VC of t equal to 0, looking at that solution over there, I'm going to get what? I'm going to get VOC plus VC of 0 minus VOC times e to the 0. And you can see right away that this guy's going to do what? This guy and that guy are going to cancel. So I get VC of 0 minus. Right? It should match. And if I look at the other boundary condition, t equal to infinity, I'm going to get VOC plus e to the minus infinity. Yeah, there's a constant there, but it doesn't really matter. That whole term goes to 0, so I get VOC. So it satisfies the solution at the boundaries. Of course it does. We expected that. Now the other thing here that we want to talk about is we want to talk about charging versus discharging caps. Maybe I should be doing this just so that we get that nice and clean. So the first thing that we want to look at here, so if I'm talking about a charging cap, this implies here, now let's look at the solution here. Look at it right here. That means that VOC has to be larger than VC of 0 minus. So charging means that I'm going that VOC is larger than VC of 0 minus. Now, physically, if you just plot this thing, what we see here is that, of course it does. Right? I'm going to assume that I have an uncharged capacitor, so I'm going to say that this is VC of 0 minus, and then this guy is going to come all the way up. And so as it comes all the way up to here, this is approaching the Thevenin voltage, or VOC value, when I'm plotting VC of t. So when I look at that, this is clearly larger than this one. Okay, what does that mean mathematically? So if I'm looking at this thing mathematically, I look at this solution here, what you're going to see here is that I have VC of t, and I got VOC, then I get this quantity, which is VC of 0 minus VOC e to the minus t over tau. So what I want to pay attention to here is that I want to define a quantity. And that quantity I'm going to call delta V. Okay? So I'm going to define delta V as what? The change in the capacitor voltage. And when I do that, look what I'm going to do. I'm going to do absolute value. So then it's going to be VC of 0 minus VOC. So this guy is a positive quantity. It's always positive. Now, look at this equation right here. If VC is smaller than this, there has to be a negative sign there. So what I'm seeing here for charging, this implies here that VC of t must be VOC minus delta V e to the minus t over tau. Okay? It has to be that way. So what I want you to pay attention to here is that if you calculate a circuit with a capacitor where I get a minus sign, that means that it's charging. So that means when I look at that delta V is this distance right here. That's what delta V is. And if I was to physically interpret this, that negative sign is essentially that somebody with an external force is taking that capacitor and it's pushing it against the electric field of the circuit. In other words, if I was to go draw a picture, you could imagine here that I have a source here. So if I now try to draw a picture with this, you imagine that I have my Thevenin voltage. Remember, this is a very simplistic view. Right? So this guy here essentially represents my Thevenin voltage, or VOC. So when I look at this guy here, what I'm seeing here is that the capacitor is at a lower voltage. So if I come over here and I look at my capacitor, I'm going to say, okay, here's my cap. So my cap starts off right here, right? Here's my cap. And what am I doing? I am forcing charge onto that cap, and this cap climbs up higher up here. And so as it climbs up higher, the distance from here to here is now delta V. So I'm going against the electric field in this direction here. So let me make sure I get the right color. So I'm seeing my cap go in that direction. Right? And what I would say here is that this is what? negative work. Right? I'm doing negative work. That means that the field is in opposite to the displacement. And so I'm putting energy into that cap. I'm moving it up that field. That's why I have that minus sign right there. So it may look counterintuitive, but if you step back, I'm going against the electric field as I push it up my circuit here. And so I always get that negative sign. But this is what I mean by that. In a very analogous way, I can do the same thing with a discharging. So if I look at a discharging cap, then this implies here that VC of 0 minus is greater than VOC. Right? If it's discharging. So if I go here and I look at the picture of this thing, I could imagine that I have a circuit that goes like this. I'm coming in, right? I'm coming in at some value, and this value is VC of 0 minus, and then this guy discharges to some value here. And what value must it discharge to? VOC. Right? It's being forced to VOC here. And so what you're seeing here is that now there's a drop in this guy. And what am I calling this drop right here? I'm calling it delta V here. Right? Delta V is this difference. But this time, look at the sign here. Since that's bigger than this, I get a plus sign. So when I write the solution for this thing, we can see here is that VC of t, I'm going to get VOC plus delta V e to the minus t over top. So the big number here is that plus sign. The big number here is that minus sign. Okay? And so the question is, why is this thing plus? Well, I'm going to go back and draw me a picture to interpret this. So if I go in to interpret this thing here in a very analogous way, you can imagine that I have a field like this again, right? And what's this field of the circuit? The potential difference produced by this field here is again my VOC here. So what is the capacitor doing? Well, it's discharging. It's going from a higher potential down to a lower potential. In other words, on my inclined picture here, you can imagine that I have my cap, and what's it doing? There is positive work here by the E field. The charge is going from a higher potential, I said charge. The cap is going from a higher potential to a lower potential. Right here, I have to do work. I have to add energy to the system because nothing will go up towards a positive charge because that's not the way it happens. Positive charge only flows from the high to the low potential. Here, there's an opposite flow. There's positive work. And that positive work means that there's a lower value here. So every time I see a discharging cap, I better see that plus sign right there. Right? That's what I mean when I look at this thing. Now, another thing that we want to look at here is that we want to look at, the next thing we want to look at is we want to look at time constant. So, as we already know about time constants from your Physics 4B class, the time constant essentially tells us how a capacitor charges up relative to time. Right? So this guy tells us how a cap charges up relative to time. Now, we can write this solution here. So when I try to interpret this solution that we wrote right here, remember, I think this solution form is best mathematically. I'm always going to solve it this way. But if I'm going to physically interpret it, I'm not going to write it this way. And one of the things that you want to pay attention to here is that look at that VOC, look at that VOC. I'm going to combine those two terms. So what you're going to find here is that I'm going to write VOC. So if I look at this guy, it looks like this to start with. But what I really want to write it is I want to write it like this here. And what I'm going to say is that to keep in the form of standard differential equations, I'm going to call this guy the natural response. This guy here is the forced response. And what you're seeing here is that this guy's doing what? It's discharging from its initial value very, 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 very quickly because it's exponential decay. And this guy is being forced to charge up to VOC very, very, very quickly. And so when I look at this thing in terms of times here, so just to make sure that we're clear, so the natural response implies here is that it tells us how the cap's initial voltage discharges. Okay, tells us how the cap's initial voltage discharges. And then this guy tells us what? How the cap charges up. So when we look at this thing here, we could set up a table to tell us how quickly this stuff happens here. So if I do this, what you'll find here is the following thing here. So now I'm going to set up a table of charging / discharging times. So if I set up this table here, I'm going to have my time constant tau. Let's say, let me be careful. Yeah, time constant. I don't know if it should be in units of seconds, of course. Then I'm going to have my VC of 0 minus e to the minus t over tau. And then this, you know what, let me be more careful about this. No, I'm going to leave it like this. No, I'm going to change my mind. Give me a little bit more time and I'll change it again. I think this is the better way to write it. So what you're seeing here is that you're seeing the following thing here. When I look at this solution for the natural response, well, it's an exponential term. When I look at the solution for the forced response, it's 1 minus that. The value of VOC, or the value of C0 minus, is not the important thing. What is important are those values right there. And so typically, when we call this just a time constant of tau, 1 tau, then I'm going to look at 2 tau, then I'm going to look at 5 tau. I could go more than this, but I think you'll get a feel for what's going on here. So when something discharges as a function of 1 tau here, it falls off from its initial value down to 37%. So you could imagine here that if I have VC of 0 minus equal to 10 volts, this guy's going to fall down to what? After 1 tau, it's going to fall to 3.7 volts. Whereas, if I look at this guy right here, this guy has to be just the opposite. It has to be 63%. So then, if I look at that VOC value, if I set that to 10 volts, after 1 time constant, it's at 6.3 volts. So you're getting these things to decay really fast. And after 2 time constants, by the way, the time constants that we may be talking about in the lab here is we're talking 10 microseconds. So within 10 microseconds, this thing has fallen this much. And then if you go to 2 tau, it's 1.4%. This is, oops, no, it's 14%, excuse me. This is 86%. And if I go to 5 tau, it's 0.7%. And this is 99.3%. So you can see that at 5 tau, the circuit is effectively charged. Now note, to get that other 0.7, it's going to take some period of time. And I don't know whether you did this in 4B, whether you had a non-leaking capacitor with a really large time constant. If you timed that thing, and to see how slowly it actually goes from this value to actually to, let's say, 10 volts, for example, it being VOC. It takes a while. And so one thing that you may have done here is that you may have just timed it, and then you just let the circuit go. And when you're letting this thing go, you'll see that that time takes a long time. So when I'm thinking about the time constant, this is what I mean. This is what I mean about the behavior of this thing. How quickly does it decay from its initial value? How quickly does it charge up to its final value? That's the power of the time constant. Now, of course, we could play with the value of R, or we could play with the value of C to change the value of that time constant, but I don't care how you play with it. This has to happen right here. And so this picture then tells us the picture that we talked about before. So this picture, what it says here, so I'm going to look at VC. Actually, let me change this a little bit. So if I have VC of T, then when I'm really looking at this guy here, I can have a value that comes in like this and then charges up. Right? So how quickly does it go from here to there? Well, one thing that you want to pay attention to is note that this is a very steep slope. Why is it steep? Because look at this thing. This thing was at its initial value, but now this thing is charging up to a new value very, very, very quickly. So you can imagine I have a switch, and now I have a 10, let's say a 10 microsecond time constant. After 10 microseconds, this thing went from 0, the way I drew it, all the way up to 10 volts. Excuse me, all the way up to 6.3 volts in 10 microseconds. By the time you hit 50 microseconds, you can see that here the slope is definitely less steep. So as a consequence, the charging gets slower and slower after this. That little bit takes the most time, but at 1 tau, that thing's jumping instantly. Now if I look at the, what you're going to find here is that if I now look at the voltage across the resistor, Well, the voltage across the resistor, by the way, I should have done this a little bit better. And then, of course, there's this discharge factor. And that discharge says exactly the same thing. How fast is it going to decay? So then now I have VOC exponentially, and then I have the new value that it's going towards. And it behaves exactly the same way. The resistor that's in series with the Thevenin circuit actually behaves differently. It goes like this, and then you'll see there's a discontinuity, and it comes like that. Now, let's just look at this guy here just a little bit, just to make sure that we're talking about the same thing. Now, remember what we said. VC of 0 minus has to be the same as 0 plus. So when I look at my circuit right here, this guy is continuous at that point, right? Between those 2 points. Continuous, it's piecewise continuous. When I look at the resistor, if you remember the resistor, we have VTH, RTH, and then I have the cap. So the voltage across the cap is related to what? The current of the capacitor. But one thing we said very clearly here is that the current of the capacitor is usually not equal to the current of the capacitor after the switch is thrown. And so what you're seeing in this case here is that this continuity right here, you can see that I go from here down to here. There's an instantaneous jump. It's discontinuous. And that's because of this scenario right here. So I think I'm done with the cap now. So when we go to analyze these circuits, you've got to be thinking about these things, right? You've got to be thinking about these things. Because you know what? I'm going to ask you these questions on the quiz and the exam. I'm going to say, step back, tell me what the hell is going on. So, what do you got to pay attention to? The charging and discharging. If I got a minus sign, I know I'm charging. Why am I charging? Because I'm pushing that cap up against the electric field. That's why that minus sign is there, but I get that jump that's there. So looking at the coefficient of the exponential term tells you that. If I'm discharging, you'll see that this thing's falling here. That plus sign says that that capacitor is moving down the potential fields here. And then when we start looking at the time constants, what this time constant is really telling us what? How quickly it's discharging from its natural value to its new value. It's being forced to VOC. How is it being forced to VOC? Like this. That's how it's being. How quickly is this discharging? Like this, relative to this time constant here. Okay, so what I want to do here is that let's look at the some strategies for solving these circuits, and then let's do 2 examples. So what am I going to do? I go to the example webpage. I'm going to go to the example webpage, first order constant. Okay? So when I hit this first order constant, I get these things here. So it's essentially what? A 4-step process. Okay? What do I mean by the 4-step process? I want to determine the capacitor's VC0 minus before the switch is thrown. Whether the switch is thrown open or closed, by the way, that's one of the easiest errors. Instead of the switch being open, you closed it. Man, I hate that. But I thank you for it too. So now, after the switch is thrown, I convert it into a Thevenin circuit. That means what? Remove the cap, get VOC, get RTH, and then calculate the time constant 1 over tau. I don't care about tau normally. Why? Look where it's at. It's 1 over tau that's in the equation, not tau. So calculate 1 over tau. And then I put it into solution form. Once I got into solution form, I then unfold my circuit, and then I go back and I calculate things. Okay? That's the process. And that's effectively what I did over here, but now here I'm being more concise.